The universe is expanding right now. Every galaxy beyond our local group is moving away from us, and the speed of that separation can be measured. Scientists have two independent ways of measuring it. Both methods are rigorous. Both rely on decades of refined technique. And they disagree with each other by roughly 8%. That might not sound like much. But in physics, an 8% discrepancy between two precise, independent measurements of the same thing is not a rounding error. It is a signal, and that signal has been growing louder for years. Adam Rees, a Nobel Prize-winning astrophysicist at Johns Hopkins University, has spent much of his career measuring the expansion rate of the universe. He is not a person prone to overstatement, and yet, when asked about the discrepancy in his data, he said plainly that we may have misunderstood the universe, not as a rhetorical device, as a conclusion drawn from his own measurements. The number at the center of this argument is called the Hubble constant. It describes how fast the universe is currently expanding. More precisely, it tells you how much faster a galaxy is moving away from you for every 3.26 million light-years of distance between you and it. One number, one universe. Two completely different answers depending on how you measure it. The first method reaches back almost 14 billion years. The European Space Agency's Planck satellite spent roughly 4.5 years mapping the cosmic microwave background, which is the faint glow of radiation left over from when the universe was only about 380,000 years old. At that point, the universe had cooled just enough for atoms to form, and light was finally able to travel freely through space. That light is still traveling today, stretched into microwave frequencies by billions of years of expansion, and it carries an extraordinarily detailed imprint of the early universe's temperature and density. From that map, physicists extracted the physical conditions of the early universe, plugged them into what is called the standard cosmological model, and calculated what the expansion rate should be today, after nearly 14 billion years of evolution. The answer was about 67 kilometers per second per megaparsec. A megaparsec, for reference, is about 3.26 million light-years. So for every 3.26 million light-years you look outward into space, galaxies are moving away from us 67 kilometers per second faster. The Planck result came with a tiny margin of error and an extremely high confidence level. It was considered one of the most precise measurements in the history of astronomy. The second method doesn't reach into the past, it measures the present directly. Rees and his team, a collaboration called SH0ES, built what astronomers call the cosmic distance ladder. The idea is straightforward, even if the execution is extraordinarily difficult. You measure the distance to nearby objects using one technique. Use those objects to calibrate a second technique that works at greater distances. And then keep stepping outward, each rung of the ladder reaching farther than the last. The process starts with pulsating stars, called Cepheid variables. These stars expand and contract in a regular rhythm, and the speed of that rhythm is directly tied to how intrinsically luminous the star is. A Cepheid that pulsates slowly is genuinely brighter than one that pulsates quickly. This relationship, discovered in 1912 by astronomer Henrietta Swan Leavitt, means you can observe the pulse of a Cepheid star, calculate how bright it truly is, compare that to how bright it appears from Earth, and work out exactly how far away it is. The dimmer it looks relative to its true brightness, the farther away it must be. From Cepheid distances, the SH0ES team stepped outward to a different class of object, type Ia supernovae. These are white dwarf stars in binary systems that accumulate mass from a companion until they hit a critical threshold and explode. Because they all explode at roughly the same mass, they all release roughly the same amount of energy. That makes them what astronomers call standard candles. You can spot a type Ia supernova hundreds of millions of light-years away. And because you know approximately how bright it truly is, you can calculate the distance to the galaxy that hosts it. Combine those distances with measurements of how fast those galaxies are receding, and you get the Hubble constant from direct observation of the present-day universe. The SH0ES team's answer was about 73 kilometers per second per megaparsec, 67 from the early universe, 73 from the present universe. In a field where measurements are routinely precise to within 1%, a gap of 8 or 9% between two rigorously independent methods is deeply significant. This disagreement has a name. Cosmologists call it the Hubble tension, and it has been one of the most debated problems in physics for nearly a decade. The history of the Hubble constant is actually a long history of disagreement. When Edwin Hubble first measured the expansion of the universe in 1929, his estimate was so far off that it implied the universe was younger than the Earth. That was an obvious problem. For decades after, two factions of astronomers argued intensely about whether the true value was closer to 50 or closer to 100 kilometers per second per megaparsec. The fight was bitter enough to split the field in half for most of the 20th century. By the early 2000s, better instruments and larger data sets finally brought consensus. The value appeared to be around 70, give or take a few units. The argument seemed to be settled. Then, as instruments became even more precise, a new gap opened, smaller than the old one, far more resistant to being closed. For a while, many physicists assumed someone had made a mistake. The most widely favored explanation was a phenomenon called stellar crowding. Cepheid variables tend to live in the dense, dusty disks of younger spiral galaxies, where stars are packed closely together. When an older instrument, like the Hubble Space Telescope, photographed them, the limited resolution of its cameras sometimes blended the light of multiple nearby stars together. That blending would make the Cepheids appear slightly brighter than they truly are. If a Cepheid looks brighter, you calculate a shorter distance to it. Shorter distances propagate through the entire ladder, systematically inflating the final value of the Hubble constant. If blending was distorting the Cepheid measurements, then cleaning it up should bring the expansion rate down towards 67 and close the tension. The James Webb Space Telescope was the perfect instrument to test this. Webb orbits the Sun about 1.5 million kilometers from Earth, far beyond the distorting effects of our planet's atmosphere and the thermal noise that limits ground-based observatories. Its primary mirror is 6.5 meters across, coated in gold to maximize infrared sensitivity, and it can resolve individual stars and distant galaxies with a clarity that makes older space telescopes look primitive by comparison. Its infrared cameras can cut through dust and see through the crowding that was suspected of corrupting Hubble's measurements. Adam Rees pointed Webb at the same Cepheid stars his team had been measuring with Hubble. The expectation among many astronomers was that Webb would gently deflate the crisis. Its superior resolution would reveal the blending that older instruments had missed. The Cepheids would look slightly dimmer through Webb's eyes. The distances would stretch outward. The Hubble constant would drop back towards 67. Some scientists were already treating the tension as a known instrumental artifact waiting to be corrected. That is not what happened. Webb confirmed Hubble's Cepheid measurements with extraordinary precision. The stars looked the same, the distances held, the expansion rate stayed near 73. In early 2024, the SH0ES team published a paper in the astrophysical journal Letters, reporting that they had now extended their Cepheid observations with Webb all the way out to a galaxy called NGC 5468, located about 130 million light-years from Earth, studying roughly 1,000 Cepheids across 5 galaxies, hosting 8 Type Ia supernovae. The conclusion was stated plainly. Systematic measurement error had been ruled out with high confidence. The tension was not a mistake. It is real. What this means physically is not entirely clear, but the possibilities are striking. If the universe is genuinely expanding at 73 kilometers per second per megaparsec rather than 67, then something between the Big Bang and now is causing it to accelerate in a way the standard model did not predict. Several candidates have been proposed. One possibility involves dark energy. The standard model treats dark energy as a cosmological constant, a fixed, unchanging energy density of empty space that pushes the universe apart at a steady rate. But if dark energy has changed over time, if it was weaker in the early universe and has grown stronger since, it could explain why the present-day expansion rate is higher than the early universe prediction. Some physicists have proposed a dynamic form of dark energy called quintessence, a hypothetical field that evolves over time rather than remaining constant. Another possibility involves new physics in the early universe itself, something that briefly altered the expansion rate before the cosmic microwave background radiation was released, leaving a slightly different fingerprint in that ancient light than the standard model predicts. Various models involving early dark energy, extra-relativistic particles, or modified gravity have been proposed to fill this gap. A third possibility is that the standard model contains a subtle error in its predictions, something that generates the correct answer for most observations, but breaks down at the specific conditions needed to extrapolate the expansion rate from the early universe to today. This would require a modification to the underlying physics of how the universe evolved, not just a change in one parameter. None of these explanations is firmly established. That uncertainty is the point. The tension itself has become a research program, driving a new generation of experiments designed specifically to nail it down. But the Hubble tension is not the only thing Webb has uncovered. In 2023, as Webb's first deep field images were analyzed in detail, a peculiar population of objects appeared in the data that had not been predicted. Astronomers called them little red dots. They were compact, intensely red sources scattered throughout some of Webb's earliest observations of the deep universe. Their spectral signatures were strange. Some appeared to show properties consistent with both active galactic nuclei and with young star-forming regions. Two completely different phenomena normally found in different kinds of objects. Initial analysis suggested that some of these objects might be extremely massive, star-forming galaxies from when the universe was less than 1 billion years old. If that were true, they would be more massive than the standard model allows galaxies to be that early in cosmic history. The cold dark matter model, which is the gravitational scaffolding underlying standard cosmology, places strict limits on how quickly matter can collapse and how rapidly galaxies can grow in the early universe. Galaxies that are too big too soon are a direct challenge to those limits. The response from the field was swift and careful. Several research teams worked to reanalyze the spectra of these objects, and a competing interpretation emerged. Many of the little red dots may be active galactic nuclei surrounded by compact host galaxies, rather than extremely massive star-forming systems. The spectra were consistent with material falling into supermassive black holes, producing the distinctive signatures of quasar activity. Sandro Takela at the University of Cambridge was among the researchers who argued that removing this alternative interpretation from the sample substantially reduced the apparent discrepancy with the standard model. The crisis over little red dots was declared resolved by some. Others noted that even after that correction, the number of massive early galaxies in Webb's data still exceeded the standard model's predictions, though not by enough to be called a fundamental contradiction. What continued to accumulate in the data, however, was a broader and more persistent pattern. The early universe, as seen by Webb, is producing galaxies that are more massive, more structured, and in some cases more morphologically mature than cosmological simulations predicted they would be at those epochs. In early 2025, Webb discovered a large spiral galaxy existing within the first 2 billion years of the universe. Spiral structure takes time to develop. The orderly, rotating disk, with its sweeping arms, requires relatively calm gravitational dynamics, not the chaotic and violent merging events that theorists expect to dominate the young universe. Astronomers noted that this galaxy either assembled its mass in an unusually efficient and orderly way, or it formed most of its stars in place, in a single extended cloud of gas. Without the galaxy mergers that typically build large systems, either interpretation requires adjustments to how we model early galaxy formation. Separately, a research team at Cambridge studied more than 250 galaxies from that same early era using Webb data and found a very different pattern in most of them. The majority of those galaxies were chaotic, clumpy, and turbulent, lacking the smooth, rotating disks of mature systems. So the early universe presents a paradox within itself. Most young galaxies behaved exactly as expected, messy and disorganized, while a minority appear to have achieved a structural maturity far ahead of schedule. Both populations appear to exist simultaneously in the same cosmic epoch. That coexistence is not something the standard model handles gracefully. And then there are the shapes. A study published in Nature Astronomy in late 2025, led by Alvaro Pozo, and including researchers from the Massachusetts Institute of Technology, Harvard University, and National Taipei University of Technology, analyzed the morphology of young galaxies observed by Webb, and found that a significant fraction of them appear elongated. Not round, not disc-shaped, but stretched out like cosmic rods or cigars. The technical term is prolate morphology. This matters because the standard cold dark matter model predicts that the large-scale structure of the universe, the vast cosmic web of filaments and voids where galaxies form, should produce galaxies with broadly spherical or oblate shapes in the early universe. Prolate galaxies are an exception rather than a rule in those simulations. Alternative dark matter models generate different predictions. In warm dark matter models, the dark matter particles have slightly more thermal energy than in the cold model, smoothing out small-scale structures and creating filaments that are more coherent and extended. In wave dark matter models, which treat dark matter as a quantum field rather than a collection of classical particles, similar structural differences emerge. Both alternatives produce conditions more conducive to forming elongated galaxies along the smooth threads of the cosmic web. Cold dark matter is not just one parameter in cosmology. It is the scaffolding that determines where and how galaxies form, how galaxy clusters assemble, what the distribution of matter looks like across the largest observable scales. If dark matter particles have different properties than the cold model assumes, the downstream consequences would propagate through nearly every prediction the standard model makes. The mass distribution within galaxy clusters would shift. The expected abundance of dwarf galaxies around larger galaxies would change. The way gravitational lensing bends light around massive objects would be subtly altered. None of these changes is dramatic in isolation, but collectively, they represent a potential restructuring of fundamental assumptions. There is a second, quieter tension that runs parallel to the Hubble problem. It is called the sigma-8 tension, sometimes written S8, and it concerns the clumpiness of matter in the universe. The standard model predicts a specific level of clustering in how matter is distributed across space. When astronomers measure that clustering directly, using gravitational lensing surveys and galaxy clustering statistics, they consistently find slightly less of it than expected. Adam Rees has referred to this as the little sibling of the Hubble tension. Less dramatic, less widely discussed, but persistent across multiple independent measurement techniques. If both the Hubble tension and the sigma-8 tension are real, and if they turn out to be symptoms of the same underlying cause rather than two unrelated anomalies, the implications for the standard model would be substantial. Two independent fractures in the same framework are harder to explain away than one. To be precise about what this situation actually means, the standard cosmological model is not failing. It is not being abandoned. It still explains the cosmic microwave background with extraordinary precision. It accurately predicted the abundance of hydrogen and helium produced in the first few minutes after the Big Bang. It accounts for the large-scale clustering of galaxies across hundreds of millions of light years. It correctly predicted the existence of dark matter halos around galaxies and the overall geometry of the observable universe. No competing theory comes close to matching its explanatory track record. What it is doing is developing fractures, cracks that were not present a decade ago and that have been widening as instruments have become more powerful. The fractures are real. They are measured. They are documented in peer-reviewed literature, and they do not go away when you look more carefully. This is the nature of mature science operating at its limits. The standard model was developed primarily in the latter half of the 20th century, refined through the 1990s and 2000s, and has performed remarkably well for decades. It is a framework built on the physics we understand, extended to describe a universe that may contain phenomena we do not yet understand. New instruments are addressing these questions from multiple directions simultaneously. NASA's Nancy Grace Roman Space Telescope is designed to conduct wide-field surveys of the sky, specifically aimed at characterizing dark energy, mapping the distribution of matter across cosmic scales, and tracking how that distribution has changed over time. The European Space Agency's Euclid mission is already mapping the geometry of the universe on a scale no previous survey has attempted, covering billions of light years of cosmic structure to measure how matter clusters and how that clustering has evolved. Future data releases from the Gaia Space Telescope will provide geometric parallax measurements precise enough to calibrate Cepheid distances independently of any assumptions about stellar physics, potentially removing one of the last contested rungs in the cosmic distance ladder. The Atacama Cosmology Telescope has already produced the most detailed ground-based map of the cosmic microwave background ever made, slightly revising the Planck estimate of the expansion rate upward, but not far enough to close the gap with direct measurements. Each of these projects is designed not just to collect more data, but to test specific predictions and assumptions that are currently contested. Science in this mode is not seeking confirmation. It is seeking contradiction, specifically the contradictions that will force a deeper understanding. The broader history of cosmology provides relevant context here. In the 1990s, the field faced a different but equally serious crisis. Measurements of the ages of the oldest stars suggested they were older than the universe itself. That is a logical impossibility. Stars cannot be older than the thing they are made of. The measurements implied a universe roughly 10 to 12 billion years old. The oldest stars appeared to be 15 billion years old or more. The discrepancy was not subtle, and it had no clean resolution within the models of the time. Then came the discovery that the expansion of the universe is accelerating. In 1998, two independent teams of astronomers studying Type Ia supernovae at large distances found that the universe is not just expanding, it is expanding faster and faster over time. That required a new ingredient, dark energy, a form of energy intrinsic to empty space that counteracts gravity on the largest scales and drives the expansion to accelerate. Once dark energy was incorporated into the standard model, the apparent age problem dissolved. A universe dominated by dark energy expands more slowly in its early stages and accelerates later, making it older than a non-accelerating universe of the same current expansion rate. The stars fit inside the universe again. What had looked like a fatal inconsistency turned out to be pointing directly at a new and fundamental component of the cosmos that nobody had anticipated. The discovery of dark energy earned Adam Rees and his collaborators the Nobel Prize in Physics in 2011, and it changed cosmology permanently. The current situation may follow a similar pattern, or it may not. That is the honest state of the field. The Hubble tension and the anomalies from Webb are real measurements. They are not going away. They are not explained by known systematic errors. The most likely resolution involves something in the physics that the standard model does not currently include. Whether that something is a modified form of dark energy, a new behavior of dark matter, new physics in the early universe, or something genuinely unexpected is not yet known. What is known is that two of the most powerful space observatories ever built are now measuring the same physical quantities and finding consistent results that the best available theory cannot fully account for. The instruments are working, the data are clean, the discrepancy is real. Rias stated carefully in December 2024 that the gap between the observed expansion rate and the predictions of the standard model suggests our understanding of the universe may be incomplete, and that two NASA flagship telescopes now confirming each other's findings means the problem must be taken seriously. This is the character of a field operating honestly at the edge of its knowledge. There is no panic in the cosmological community. There is no collapse of confidence in the underlying framework. What there is, instead, is a focused and productive anxiety. The kind that comes when a well-tested model meets data that it cannot fully absorb. The universe is about 13.8 billion years old, give or take. It began in an extraordinarily hot, dense state, expanded and cooled, formed the first hydrogen and helium nuclei within the first few minutes, released light when it was 380,000 years old, grew filaments of dark matter that collected gas and collapsed into the first stars after a few 100 million years, and has been building galaxies, clusters, superclusters, and vast voids ever since. That story is not in question. The evidence for it is overwhelming and diverse. What is in question is whether the equations governing that story are exactly right, or whether they are a very good approximation to something deeper and more complete. Every major advance in fundamental physics has involved the discovery that a successful theory was the limit of a more general one. Newtonian gravity was not wrong. It was an approximation to general relativity that works at low velocities and weak gravitational fields. Classical mechanics was not wrong. It was the limit of quantum mechanics in the regime of large, slow objects. The standard cosmological model may be similarly situated, an extraordinarily successful framework that is accurate across most of the observable universe, and yet contains within it the seeds of the theory that will eventually replace or extend it. The measurements being made right now with Webb and its companion observatories may be detecting those seeds. The slight excess of massive early galaxies, the elongated morphologies, the Hubble tension, the sigma-8 tension, the puzzling properties of the little red dots, none of these is individually enough to overturn the model. Together, they suggest that something in the foundations is slightly off. Finding out what that something is will likely require not just better measurements, but a new conceptual framework, a different way of thinking about dark energy, or dark matter, or the conditions of the very early universe. These frameworks are being developed now. Competing models are being tested against Webb's data every year. Papers proposing extensions to the standard model appear weekly in the astrophysical literature. The scientific community is not in crisis. It is in the productive tension of a field that has pushed its current tools to their limit and is now confronting the boundary of what it knows. That boundary is not a wall, it is a threshold. In the coming years, as Roman and Euclid complete their surveys, as Gaia refines its parallax catalog. As the Vera C. Rubin Observatory begins its decade-long survey of the southern sky, and as theoretical physicists continue to develop and constrain alternative models, the picture will sharpen. Either the tensions will dissolve under the weight of better data, revealing a systematic error or a bias no one has yet identified, or they will deepen and sharpen into a genuine contradiction that demands new physics. Both outcomes are scientifically valuable. Both push understanding forward. The universe is not broken. The standard model is not failing. But it is telling us, in the language of numbers and discrepancies and anomalous morphologies, that there is more to understand than we thought. That message, coming from the farthest reaches of the observable cosmos, delivered by photons that have been traveling for billions of years to reach a mirror floating in the cold of space, is not a cause for alarm. It is an invitation. The James Webb Space Telescope has given us a view of the early universe, more detailed and more precise than anything ever achieved before. And that view has shown us not a confirmed picture of a well-understood cosmos, but a richer and more complicated one than our best models predict. Early galaxies that are larger than expected, shapes that don't match simulations, an expansion rate that depends on how you measure it, a universe that behaves in subtle but measurable ways, differently than the equations say it should. Whatever comes next in cosmology will be built on these observations. The physicists and astronomers working on these problems today are not dismantling what we know. They are extending it. They are following the data wherever it leads, which is what scientists have always done at moments like this. The history of physics is a history of surprises, of theories that worked until they didn't, and of the deeper theories that emerged from the failure. The photoelectric effect that classical electrodynamics couldn't explain became the seed of quantum mechanics. The orbit of Mercury that Newtonian gravity couldn't quite account for became the test that confirmed general relativity. The expanding universe that seemed to violate energy conservation became the evidence for dark energy. Every time the universe has refused to fit neatly into the current model, the result has been a more complete understanding of how reality works. The James Webb Space Telescope is not showing us that cosmology has failed. It is showing us where cosmology ends and where the next version of it will have to begin. That boundary is one of the most exciting places in all of science, and right now, we are standing at it. To understand why the Hubble tension matters so deeply, it helps to understand exactly what the Hubble constant represents in physical terms, and why its value is not just an interesting number, but a description of the entire history and future of the cosmos. Edwin Hubble published his observations of galactic redshifts in 1929. By measuring how much the light from distant galaxies was shifted toward longer, redder wavelengths, he demonstrated that virtually all galaxies beyond our local neighborhood were moving away from us, and that the farther away a galaxy was, the faster it was receding. This was not Hubble's idea alone. The Belgian mathematician and priest Georges Lemaitre had actually published a version of this relationship 2 years earlier, in 1927, deriving it from Einstein's equations of general relativity. But Hubble's observational data made the case empirically undeniable. The relationship Hubble observed was strikingly simple. Velocity equals a constant times distance. Double the distance, double the recession speed. This is exactly what you would expect if the universe began in an extremely hot, dense state and has been expanding ever since. Every point in space is moving away from every other point, not because galaxies are traveling through space in the conventional sense, but because the fabric of space itself is stretching. A photon of light leaving a distant galaxy today will arrive at Earth millions or billions of years from now. And during that journey, the space through which it travels will continue to expand, stretching the photon's wavelength and shifting it toward the red end of the spectrum. The proportionality constant in Hubble's relationship, the number that connects velocity to distance, is what we call the Hubble constant. It has units of kilometers per second per megaparsec, which sounds technical but is simply a statement of how much faster a galaxy recedes for each additional unit of distance. Its value determines how old the universe is, how large the observable universe is, and how the cosmos will evolve in the far future. In the context of the current tension, the difference between 67 and 73 kilometers per second per megaparsec corresponds to a difference in the calculated age of the universe of roughly 1 billion years. If the expansion rate is genuinely faster than the early universe prediction implies, the universe is younger than we thought. If it is slower, the universe is older. 1 billion years is not trivial. It represents billions of stellar lifetimes, the time it takes for multiple generations of stars to live and die, and seed the galaxy with the heavy elements needed for rocky planets. Getting the age right matters for everything downstream. Hubble's original estimate for the constant, published in 1929, was about 500 kilometers per second per megaparsec. That number implied a universe only about 2 billion years old, far younger than the Earth, which was already known from radioactive dating to be about 4.5 billion years old. The contradiction was glaring. Stars had to form somewhere, and they needed time. Galaxies needed time to assemble. A universe 2 billion years old could not plausibly contain a 4.5 billion year old planet. Something was wrong. The problem turned out to be in the distance measurements. Hubble had conflated two different types of variable stars, Cepheids and a class of pulsating stars called W Virginis stars, which are intrinsically less luminous than Cepheids. By treating them as equivalent, he systematically underestimated distances to nearby galaxies, which caused him to overestimate the expansion rate. In the 1950s, astronomers Walter Baade and Alan Sandage began correcting these errors, and the Hubble constant dropped dramatically. The subsequent decades saw the value oscillate between competing measurements, with Walter Baade and then Sandage favoring values around 50, while Gerard de Vaucouleurs consistently found values nearer to 100. The scientific argument was personal, heated, and unresolved for the better part of 40 years. By the 1990s, the Hubble Space Telescope Key Project, a major observing program specifically designed to settle the question, finally arrived at a consensus value of about 72. With an uncertainty of about 8 kilometers per second per megaparsec in either direction, the field breathed a collective sigh of relief. The measurement seemed nailed down, but as the uncertainty shrank with better instruments and more data, the consensus began to fracture in a new way. The split was no longer between values of 50 and 100. It was between values of 67 and 73, small enough to have been invisible when measurement errors were large enough to be unmistakable once the errors became small. The Planck satellite's measurement of the cosmic microwave background, published in its final data release in 2018, pinned the early universe prediction at 67.4, with an uncertainty of about 0.5. The SH0ES team's direct measurement, also updated in 2022, arrived at 73 with an uncertainty of about 1. The two error bars do not overlap. At the formal statistical language of the field, this disagreement exceeds 5 sigma, which is the threshold conventionally required to claim a discovery. In this case, the discovery is not of something new, but of something wrong. At 5 sigma, the probability that this discrepancy is a statistical fluctuation is less than 1 in 3.5 million. The standard response to tensions in physics is to look for systematic errors in one or both measurements. Systematic errors are not random fluctuations. They are biases that push measurements in a consistent direction, arising from flawed assumptions, miscalibrated instruments, or unrecognized physical effects. The history of the Hubble constant debate is largely a history of systematic errors being identified and corrected. For the early universe measurement from Planck, the main concern involves assumptions embedded in the standard cosmological model itself. The Planck result is not a direct measurement of the current expansion rate. It is a prediction derived by evolving the early universe conditions forward in time using the equations of the standard model. If those equations contain an error, or if the physics of the early universe included some process not captured in the model, the prediction would be wrong. The measurement itself might be perfectly accurate, but the conclusion drawn from it would not. For the late universe measurement from SH0ES, the concern has centered on the Cepheid distance ladder and the potential for systematic errors to propagate upward through its rungs. If Cepheids are slightly miscalibrated at any level, those errors get multiplied as you step outward to type Ia supernovae, and then to the Hubble flow. The most widely discussed source of this kind of error was the stellar crowding problem, the blending of light from nearby stars in the dense regions where Cepheids are typically found. Webb's confirmation that the SH0ES Cepheid distances are correct eliminates crowding as an explanation. Other potential systematics have also been examined and largely ruled out. Dust reddening along the line of sight to Cepheids can affect apparent brightness measurements, but modern infrared observations largely circumvent this. Chemical differences between Cepheids in calibrator galaxies and those in supernova host galaxies have been studied extensively. Alternative distance indicators, including the tip of the red giant branch method, the Tully-Fisher relation, and surface brightness fluctuations, have all been applied independently, and while they sometimes give slightly different values, none has consistently returned a result as low as 67. The Hubble tension is therefore not a problem that can be dismissed as a measurement error. It is a genuine discrepancy that has survived years of scrutiny, and now, following Webb's observations, carries even stronger observational support. What the tension implies physically remains the subject of intense theoretical work. The most conservative class of solutions involves modifying the physics of the early universe in a way that changes the conditions captured in the cosmic microwave background without affecting direct late universe measurements. One prominent idea is early dark energy, a hypothetical form of energy that contributed to the universe's expansion rate during the first few 100,000 years before the cosmic microwave background was released, and then diluted away. If early dark energy existed, it would have made the early universe expand slightly faster than the standard model assumes, which would propagate through the equations and produce a higher predicted late universe expansion rate. The predicted and measured values would then be closer to agreement. Early dark energy models have been tested against the Planck data and found to be a potential fit, but at a cost. They require fine-tuning of parameters, and they tend to worsen other aspects of the fit to the cosmic microwave background data. No early dark energy model proposed so far manages to solve the Hubble tension without creating a different problem elsewhere. A second class of solutions involves modified gravity, the idea that Einstein's general relativity is not the complete description of how mass and energy warp space and time. Many extensions of general relativity have been proposed over the years, motivated by various theoretical considerations. Some of these modify how gravity behaves over very large distances or at very low curvatures, which could alter the expansion history of the universe in ways that shift the predicted Hubble constant. Testing these models requires not just the Hubble constant measurement, but a comprehensive set of other cosmological observations, because modified gravity would leave signatures throughout the data. A third class involves the nature of dark energy. In the standard model, dark energy is represented as a cosmological constant, a term Einstein originally introduced into his equations and then famously called his greatest blunder before the discovery of the accelerating expansion rehabilitated it. A cosmological constant is entirely static. Its energy density does not change as the universe expands. It is, in essence, a property of empty space rather than a substance in the usual sense. If dark energy is instead a dynamical field that evolves over cosmic time, its properties in the early universe could differ from its properties today. A dark energy field that was slightly stronger in the distant past would have influenced the expansion history in ways that could reconcile the two Hubble constant measurements. In 2024, the Dark Energy Spectroscopic Instrument, a ground-based survey instrument in Arizona, released preliminary results suggesting that dark energy may not be behaving exactly like a cosmological constant. The data, based on measurements of how the distribution of galaxies has changed over the past several billion years, hinted at a slight evolution in the dark energy equation of state. The results were not conclusive, but they added to the evidence that the cosmological constant may be an approximation rather than a fundamental description. The Dark Energy Spectroscopic Instrument, known as DESI, is designed to map the three-dimensional positions of tens of millions of galaxies across about 14 billion light-years of cosmic history. By tracking the acoustic oscillation scale, the characteristic size of clustering in the distribution of galaxies that was set by sound waves propagating through the early universe, it can measure the expansion history of the universe across cosmic time with high precision. Its full dataset, when complete, will provide one of the most stringent tests of dark energy models ever assembled. Parallel to all of this, the Webb telescope has continued its survey of the early universe, and each data release adds detail to the picture of a cosmos that behaves slightly differently than expected at early times. One area receiving particular attention involves the epoch of reionization, the period between roughly 200 million and 1 billion years after the Big Bang, when the first stars and galaxies ionized the surrounding hydrogen gas that had pervaded the universe since recombination. Understanding when reionization happened, how quickly it proceeded, and what drove it requires knowing how many and how energetic the first sources of ionizing radiation were. Webb's ability to detect individual galaxies at these early times is giving astronomers the most direct view yet of this epoch. What they are finding is that the sources of ionizing radiation appear to have been somewhat different in character than pre-Webb models assumed. The early galaxies Webb observes at these redshifts are frequently compact and clumpy, with active star formation concentrated in small regions. Some appear to host active galactic nuclei, which contribute ionizing photons in addition to those produced by young stars. The relative contributions of stars and black holes to reionization is now a topic of active research, informed directly by Webb data, and the answer affects models of how the intergalactic medium evolved during the universe's first billion years. The supermassive black holes at the centers of some of these early galaxies are themselves a puzzle. The standard theory of black hole formation involves the collapse of massive stars into stellar mass black holes, followed by billions of years of gradual growth through accretion of surrounding gas and mergers with other black holes. Growing a black hole to a mass of hundreds of millions or billions of solar masses takes time under this scenario. Yet Webb is finding supermassive black holes of that scale in galaxies that existed within the first billion years of the universe, far too early for them to have grown through gradual accretion alone. Several proposed solutions to this problem have been put forward. Direct collapse black holes are one option. Under the right conditions in the early universe, gas clouds could have collapsed directly into black holes of 10,000 to 100,000 solar masses, bypassing the stellar phase entirely. These would provide a much larger starting point for subsequent growth. Rapid accretion at rates exceeding the traditional Eddington limit, which is the theoretical maximum accretion rate set by the radiation pressure of infalling material, is another possibility. Some simulations suggest that under the conditions prevailing in dense early universe environments, gas could funnel into black holes fast enough to build supermassive objects within a few 100 million years. A third option involves the possibility that some of the objects Webb identifies as supermassive black holes in the early universe are actually somewhat different kinds of objects, or that their masses have been slightly overestimated. None of these explanations is yet confirmed. The early formation of supermassive black holes is one of the most active unsolved problems in observational astrophysics, and Webb is producing new data on it every year. The large-scale structure of the universe, the cosmic web of filaments, sheets, and voids that stretches across billions of light years, provides another testing ground for the standard model. The pattern of this structure, on large scales, is one of the most precisely measured quantities in cosmology. The angular power spectrum of the cosmic microwave background, the clustering statistics of galaxies, and the baryon acoustic oscillation scale all describe aspects of this structure and must be consistently explained by any model that claims to describe the universe correctly. On very large scales, the universe appears statistically uniform. The cosmic microwave background looks essentially the same in every direction, with temperature fluctuations of only about 1 part in 100,000. The large-scale galaxy distribution, when averaged over sufficiently large volumes, also appears uniform. This uniformity is one of the foundational assumptions of standard cosmology, called the cosmological principle. Recent surveys of the galaxy distribution have found some structures that strain this assumption at their edges. A concentration of galaxy clusters called the Hercules Corona Borealis Great Wall, first reported in 2014, extends over roughly 10 billion light-years if confirmed, which would make it the largest known structure in the observable universe. Structures of that scale are at the boundary of what standard models predict should exist. The Sloan Great Wall, discovered earlier in the 2000s, and the Giant Arc, reported in 2021 and extending about 3.3 billion light-years across, have also been cited as potentially challenging the cosmological principle on intermediate scales. Whether these structures represent genuine violations of the principle or are statistical outliers within an otherwise uniform distribution is debated. The universe's observable volume is large enough that exceptional structures can appear even within a model that predicts statistical uniformity. What the ongoing galaxy surveys, including those from DESI and Euclid, I will provide is a much larger statistical sample from which to determine whether these large structures are within the expected distribution or genuinely anomalous. The cosmic microwave background itself carries information about the largest scales, and here too there are anomalies that have been discussed for years. The Planck data revealed several unexplained features in the very low multipole modes of the temperature power spectrum, corresponding to angular scales of 90 degrees or more. These features, including an alignment between certain modes and the geometry of the solar system, and a hemispherical power asymmetry, where one side of the sky appears slightly different from the other, were present in earlier satellite data and confirmed by Planck. They are not explained by the standard model. Most cosmologists regard them as statistical flukes, given the small number of modes at those angular scales, but they have never been definitively resolved. These large-scale anomalies, combined with the Hubble tension, the sigma-8 tension, and the morphological and structural surprises from Webb form a collection of observational challenges that individually could each be dismissed as unlikely but possible flukes, but collectively suggests that either the standard model contains systematic blind spots, or the universe contains physics that has not yet been incorporated into it. The fundamental components of the standard cosmological model, dark matter, dark energy, and inflationary cosmology, have each been extremely successful in explaining observations, and each remains without a confirmed physical identification. Dark matter was first proposed by Fritz Zwicky in 1933 when he measured the velocities of galaxies in the Coma cluster and found they were moving far too fast for the visible mass of the cluster to hold them gravitationally. The galaxies should have flown apart. Something invisible was providing the gravitational glue. Vera Rubin and Kent Ford confirmed this in the 1970s by measuring the rotation curves of galaxies, showing that stars in the outer regions of spiral galaxies orbit at nearly the same speed as stars near the center, rather than slowing down with distance, as Newton's laws predict in the absence of extra mass. The flatness of galactic rotation curves is now one of the most reproducible observations in astronomy, and it implies that galaxies are embedded in enormous halos of invisible matter, extending far beyond their visible disks. What that dark matter actually is has been the subject of intensive, experimental effort for decades. The most popular theoretical candidate for much of this period was the weakly interacting massive particle, or WIMP, a hypothetical particle with a mass roughly similar to a proton or heavier, interacting via the weak nuclear force. WIMPs were theoretically attractive because they arise naturally in supersymmetric extensions of the standard model of particle physics, and because they would be produced in the right abundance during the early universe, through a mechanism called thermal freeze-out to explain the observed dark matter density. This was sometimes called the WIMP miracle. But WIMPs have not been found. Underground detectors of increasing size and sensitivity have searched for the rare occasions when a WIMP would scatter off an atomic nucleus, depositing a tiny amount of detectable energy. The Large Underground Xenon experiment, the Panda X experiments in China, and the LUX Zeppelin detector have all set limits on WIMP cross-sections that rule out large portions of the theoretical parameter space that motivated the search. The Large Hadron Collider at CERN has not produced the supersymmetric particles that were expected to accompany WIMPs. The WIMP miracle is looking increasingly miraculous in the improbable sense. Alternative dark matter candidates have accordingly received growing attention. Axions are hypothetical particles originally proposed to solve a different problem in particle physics, the strong CP problem, but which would also make suitable dark matter candidates if they have the right mass. Axion search experiments, like ADMX, the Axion Dark Matter Experiment, are beginning to probe the relevant mass range. Primordial black holes, which are black holes that formed in the early universe from density fluctuations rather than from stellar collapse, have been constrained but not ruled out across certain mass ranges. Sterile neutrinos, hypothetical heavy counterparts to the ordinary neutrinos we know exist, have also been proposed. The warm dark matter and wave dark matter alternatives that may be suggested by Webb's prolate galaxy observations represent a different approach. Rather than proposing a specific new particle, they modify the collective behavior of whatever dark matter is, making it behave slightly differently on small scales, while preserving its successes on large scales. Wave dark matter, also called fuzzy dark matter, treats dark matter as an extremely light quantum field with wavelengths large enough to wash out structure below a certain scale, typically around 1 kiloparsec. This smooths the inner density profiles of galaxies in ways that match observations better than the cold dark matter model in some cases, while producing elongated structures in the early universe that may match what Webb is now seeing. The identity of dark matter remains one of the most important open questions in physics. It is not just a cosmological problem. Whatever dark matter is, understanding it would extend the standard model of particle physics, one of the most successful theories ever constructed, into a regime it currently cannot address. The two great standard models of physics, the cosmological one and the particle physics one, are inconsistent at this point. One says dark matter exists, the other has no room for it. The same can be said for dark energy. The energy density of empty space, if calculated from the principles of quantum field theory using the standard model of particle physics, should be enormous. The naive calculation produces a value roughly 120 orders of magnitude larger than the observed dark energy density. This is one of the most embarrassing discrepancies in theoretical physics, sometimes called the cosmological constant problem. Some symmetry principle, still unknown, must be suppressing the quantum contributions to the vacuum energy and reducing it to its observed near-zero value. Nobody knows what that symmetry is. The possibility that dark energy is not a true constant but instead a dynamical field evolving over time, suggested by the DESI results and by theoretical considerations, would make the cosmological constant problem different in character. A field that evolves could have different mechanisms to explain its current small value than a true constant. Some models invoke the landscape of string theory, where different regions of a vast number of possible universes have different values of the cosmological constant, and we necessarily observe the value compatible with the existence of galaxies, stars, and observers. This anthropic reasoning is considered unsatisfying by many physicists, but has not been replaced by a better explanation. These open questions are not peripheral. They sit at the center of physics. Dark matter and dark energy together constitute approximately 95% of the total energy content of the universe. The stuff we know, the protons, neutrons, electrons, photons, and neutrinos, described by the standard model of particle physics, amounts to roughly 5% of everything that exists. We have detailed knowledge of 5% of the universe and placeholder names for the rest. The James Webb Space Telescope is providing new observational constraints on both dark components simultaneously. By measuring the sizes, shapes, and distributions of early galaxies, it constrains dark matter models that determine how the first cosmic structures formed. By observing the expansion history of the universe at high redshifts, it potentially constrains dark energy models. By finding discrepancies with predictions, it is doing exactly what a great scientific instrument should do: mapping the edge of knowledge. There's a particular way in which Webb's observations of the very early universe are scientifically significant beyond the specific anomalies they reveal. Before Webb, the first billion years of the universe were largely inaccessible to direct observation. The most distant galaxies Hubble could observe in detail existed when the universe was roughly 2 to 3 billion years old. The first 100 million to 1 billion years were a theoretical construction informed by the cosmic microwave background and by simulations, but not directly confirmed by resolved observations of individual galaxies. Webb changed this. Its combination of infrared sensitivity and angular resolution allows it to detect and characterize galaxies as they existed when the universe was only a few 100 million years old. This means that, for the first time, the theoretical predictions about the first epoch of galaxy formation are being tested against real data, and the data is producing surprises. The surprises do not necessarily mean the theories were wrong in their foundations. They may mean the theories were wrong in their details. Galaxy formation involves a complex interplay of gravity, gas dynamics, star formation, black hole growth, and feedback processes, all operating on scales from stellar systems to tens of thousands of light years. The simulations that predict galaxy properties are sophisticated but necessarily approximate. Parameters that describe how efficiently gas forms stars, how much energy is released by supernovae and returned to the interstellar medium, how black holes grow and influence their host galaxies, these are all set by observations of the relatively nearby, relatively recent universe, and then extrapolated to earlier times. If the early universe behaved differently in any of these respects, the extrapolations would break down. Galaxies might have formed stars more efficiently when the universe was denser. Black holes might have grown more rapidly when the gas supplies were larger. Feedback from supernovae and active galactic nuclei might have had different effects on the smaller, denser galaxies of the early universe. These are not violations of fundamental physics. They are refinements to our understanding of astrophysical processes in extreme environments, distinguishing between a true cosmological anomaly, one that requires new physics at the level of the Hubble constant or the nature of dark matter, and an astrophysical anomaly, one that requires refinement of how galaxies form and evolve within the existing cosmological framework, is one of the central challenges of interpreting Webb's results. It requires not just observations, but theoretical models sophisticated enough to make the distinction, and observational datasets large enough to provide statistical leverage. Both are being developed simultaneously. The field is not waiting for one or the other. It is pushing on multiple fronts at once, which is the normal mode of a mature scientific discipline confronting an important unresolved question. Webb will continue observing for at least 20 years the design lifetime of its cryogenic fuel supply. Every year it operates adds depth to the statistical sample of early galaxies extends its surveys to new areas of the sky, and probes new aspects of cosmic evolution. Combined with the ground-based and space-based surveys coming online in the next decade, the observational foundation of cosmology will be transformed by the time the next generation of physicists inherits the field. The generation currently working on these problems knows that they may be the ones who identify the discrepancy that leads to the next great synthesis. That is a remarkable position to be in. Not every physicist gets to work at a moment when the most successful theory in the history of cosmology is showing its first genuine cracks. Not every observer gets to work with an instrument powerful enough to see those cracks forming in real time at the edge of the observable universe. The universe, as best we can measure it, is about 93 billion light-years in diameter, observable in all directions out to the cosmic microwave background. Beyond that horizon, the universe almost certainly continues, but the light from those regions has not had time to reach us since the Big Bang. We are seeing, at most, a bubble, a finite slice of what may be an infinite cosmos. Everything we know about cosmology is inferred from light and gravity, from the wavelengths of photons that have been traveling for billions of years to reach our detectors, from the bending of space by masses we cannot directly see, from the statistical patterns in the distribution of matter across scales we cannot fully comprehend in human terms. The fact that this enterprise, conducted by creatures who live for roughly 80 years on a planet that is 4.5 billion years old, in a universe that is nearly 14 billion years old, has produced a model that correctly predicts the abundances of light elements formed in the first 3 minutes, that correctly describes the temperature fluctuations and radiation from 380,000 years after the Big Bang, that correctly anticipates the distribution of galaxies across billions of light years, is extraordinary. The fact that this model is now showing seams, that measurements precise enough to reveal discrepancies of 8% in the expansion rate exist, that we can now observe individual galaxies from when the universe was only a few percent of its current age, is not a sign of failure. It is a sign of how far the enterprise has advanced. Adam Rees's statement that we may have misunderstood the universe is not pessimistic. It is the most honest and optimistic thing a scientist can say. It means the measurements are good enough to find out what we got wrong. It means the next version of our understanding is within reach. Whatever is driving the Hubble tension, whatever is producing galaxies that are too massive and too structured too early, whatever dark matter and dark energy truly are, the answers exist in the universe. The universe does not hide. It emits photons in all directions, expands at a rate that can be measured, bends light by amounts that can be calculated. Every measurement we make, no matter how unexpected its result, is information. Every discrepancy is a question with an answer. Finding those answers is the work of the years ahead. To appreciate the full significance of where cosmology stands right now, it is worth tracing the intellectual journey that led to the Standard Model and understanding what it actually claims about the universe. The 20th century produced 2 revolutionary frameworks in physics that transformed the field. The first was Einstein's general theory of relativity, published in 1915, which replaced Newton's description of gravity as a force acting at a distance with a geometric description in which mass and energy curve the fabric of space-time, and objects follow the straightest possible paths through that curved geometry. General relativity made predictions that Newton's theory could not, including the bending of light by massive objects, the slowing of time in strong gravitational fields, and the precession of Mercury's orbit. Each prediction was confirmed. The theory became the foundation on which all modern cosmology is built. The second revolution was quantum mechanics, developed through the 1920s by Bohr, Heisenberg, Schrödinger, Dirac, and others, which described the behavior of matter and energy at atomic and subatomic scales. Quantum mechanics produced the Standard Model of particle physics, which describes all known elementary particles and 3 of the 4 fundamental forces, electromagnetism and the weak and strong nuclear forces, with astonishing precision. The Standard Model of particle physics has now been tested at enormous energies by particle accelerators and confirmed in thousands of experiments. Its most recent triumph was the discovery of the Higgs boson at the Large Hadron Collider in 2012, which completed the theoretical framework's last missing piece. But general relativity and quantum mechanics are incompatible at a fundamental level. They use different mathematical frameworks, make different assumptions about the nature of space and time, and break down in each other's domains. At the center of a black hole, where both extreme gravity and extreme quantum effects operate simultaneously, neither theory gives reliable answers. At the instant of the Big Bang, when all the matter and energy of the observable universe was compressed into an almost infinitely small volume, the same problem arises. A complete theory of quantum gravity, one that unites the two frameworks, remains one of the great unsolved problems of theoretical physics. String theory, loop quantum gravity, and various other approaches have been proposed as pathways to this unification, but none has yet produced a confirmed prediction that differs from general relativity in a regime accessible to current experiments. The search for quantum gravity is ongoing, but the current cosmological anomalies are not obviously connected to it. They appear at scales and energies where quantum gravity effects should be negligible. The Hubble tension, the galaxy formation surprises, the dark matter and dark energy questions. These are almost certainly low-energy phenomena, describable in principle within a framework compatible with general relativity and quantum field theory. If only we knew the right framework. The cosmic microwave background deserves more attention as a scientific resource, because it is central to understanding what the Standard Model predicts and where those predictions might go wrong. When the universe was about 380,000 years old, it cooled below the temperature at which electrons and protons could form stable hydrogen atoms. Before this moment, the universe was a hot plasma, a fog of charged particles and photons, so tightly coupled that light could not travel freely. Every photon was quickly scattered. When atoms formed, the coupling broke. Photons decoupled from matter and streamed freely through space for the first time. This moment is called recombination, and the light released at that moment is what we observe as the cosmic microwave background. That light left the universe when it was roughly 1,000 times smaller than it is today, and it has been traveling through expanding space ever since. Its wavelengths stretched by the expansion until they now fall in the microwave region of the electromagnetic spectrum, at temperatures of about 2.7 degrees above absolute zero. It arrives at our detectors from every direction in the sky with extraordinary uniformity, varying by only about 1 part in 100,000, from one patch of sky to another. Those tiny fluctuations, measured first by the COBE satellite in 1992, then with dramatically higher precision by the WMAP satellite from 2001 to 2010, and finally by the Planck satellite from 2009 to 2013, represent the seeds of all structure in the universe. The slight density variations in the early universe grew through gravitational attraction over billions of years into the galaxies, clusters, and filaments we see today. The pattern of fluctuations in the cosmic microwave background therefore encodes the initial conditions of the universe, and by comparing that pattern to what we observe in the distribution of matter today, we can test whether the physics connecting the two epochs is correctly described by the Standard Model. The agreement between the Standard Model and the Planck data is, by any measure, astonishing. The Standard Model has about 6 free parameters, numbers that must be set by observation rather than derived from first principles. These include the densities of ordinary matter and dark matter, the dark energy density, the optical depth of the universe during reionization, the amplitude and slope of the primordial power spectrum of fluctuations, and a few others. Once these parameters are fit to the Planck data, the model correctly predicts a vast range of other observations. The abundance of deuterium in the early universe, measured from ancient gas clouds, the amplitude of large-scale galaxy clustering, the properties of gravitational lensing maps, the frequency of galaxy clusters as a function of mass and redshift. This is the success that makes the Hubble tension so significant. The Standard Model is not wrong about most things. It is wrong about one thing, the current expansion rate, and possibly slightly wrong about a few others, like the clustering amplitude and the morphologies of early galaxies. These specific failures, embedded within a framework of overwhelming successes, are the fingerprint of a theory that is almost right but missing something. In the history of physics, almost right has a specific meaning. Newtonian mechanics was almost right. It worked for every experiment performed before Einstein. Its failure was revealed only in precisely those experiments where the deviations from Newtonian predictions were large enough to measure fast-moving particles, strong gravitational fields, atomic spectral lines. The standard cosmological model may be in an analogous position. Its failures are being revealed in precisely the experiments where the deviations are large enough to measure the expansion rate of the current universe, the mass function of early galaxies, the shape distribution of young galaxies. The analogy is suggestive, but imperfect. Einstein's general relativity did not simply patch Newton. It replaced Newton with a fundamentally different conceptual framework that reduced to Newton as a special case. Whatever extends the standard cosmological model may similarly require a new way of thinking about dark energy, dark matter, or the physics of the early universe, not just a modification to existing equations, but a reconceptualization of what those quantities are. Cosmological inflation is worth discussing here because it represents the most speculative but also most consequential theoretical element of the Standard Model, the one that is most likely to be modified by a deeper understanding. Inflation is a hypothetical period of extremely rapid exponential expansion that occurred in the first tiny fraction of a second after the Big Bang, before the epoch described by standard cosmology. During inflation, the universe expanded by an extraordinary factor, perhaps 10 to the power of 26 or more, in an almost unimaginably short time. The evidence for inflation is indirect but compelling. Inflation explains several features of the universe that would otherwise require fine-tuned initial conditions. The remarkable uniformity of the cosmic microwave background across regions of the sky that could not have been in causal contact without inflation, the flat geometry of the observable universe, and the spectrum of density fluctuations that seeded all structure. Inflation predicts a specific statistical signature in the cosmic microwave background. The fluctuations should follow a nearly scale-invariant Gaussian distribution, meaning they should be present at all angular scales, with roughly the same amplitude, and with no preferred direction or position. The Planck data confirm this prediction to high precision. Inflation also predicts a background of gravitational waves from the inflationary epoch, which would leave a specific polarization pattern in the cosmic microwave background called B-modes. This gravitational wave background has not yet been detected, but experiments including the BICEP and Keck array at the South Pole are searching for it at ever-increasing sensitivity. The theoretical mechanism underlying inflation, a hypothetical field called the inflaton whose potential energy drove the rapid expansion, is entirely unknown. There are hundreds of inflationary models in the literature, differing in the shape of the inflaton potential, the energy scale of inflation, and whether inflation was preceded by some other epoch. Most of these models predict broadly similar observational signatures, making it difficult to distinguish between them with current data. The detection of primordial gravitational waves would dramatically constrain the space of viable models, because the amplitude of those waves is directly related to the energy scale at which inflation occurred. If inflation happened at high energies, close to the Planck scale, the gravitational waves would be detectable. If it happened at lower energies, they might be undetectable with any near-future experiment. The absence of a detection to date constrains, but does not rule out high-energy inflation. One connection between inflation and the current cosmological anomalies involves the possibility of anomalous features in the primordial power spectrum. The nearly scale-invariant spectrum predicted by simple inflation models is well confirmed, but subtle deviations from perfect scale invariance could in principle affect galaxy formation in the early universe, producing slightly more or slightly fewer massive galaxies at specific epochs. Whether the galaxy formation surprises Webb has uncovered are connected to inflationary physics is an intriguing but speculative possibility that requires more data to assess. Webb's observations are also contributing to our understanding of the intergalactic medium, the diffuse gas that permeates the space between galaxies. This medium is not empty. It contains hydrogen and helium, trace amounts of heavier elements, and a web of filamentary structure shaped by the same large-scale gravitational dynamics that organizes galaxies and galaxy clusters. The properties of the intergalactic medium encode information about the history of galaxy formation, because galaxies continuously expel gas through supernova-driven winds and the activity of central black holes, seeding the surrounding medium with metals and energy. By observing how background quasars' light is absorbed as it passes through intervening gas clouds, a technique called the Lyman alpha forest, astronomers can map the distribution of hydrogen across enormous cosmic volumes. The statistics of this distribution depend on the clustering of dark matter, the temperature and pressure of the gas, and the intensity of the ultraviolet background that ionizes it. Comparisons between Lyman alpha forest measurements and predictions from the Standard Model have provided some of the most stringent constraints on dark matter properties, and these constraints favor cold dark matter over warm alternatives in most of the relevant parameter space. However, the Lyman alpha forest constraints were derived primarily from observations of gas at redshifts between 2 and 4, when the universe was 2 to 3 billion years old. The Webb observations of galaxy morphology and the prolate galaxy results concern a different epoch, the first billion years, where the constraints from the Lyman alpha forest are weaker. There may be room in the data for warm or wave dark matter to explain the early galaxy morphologies without violating the Lyman alpha forest results. If the transition from warm to effectively cold behavior in dark matter clustering happens at scales and redshifts not yet well constrained by existing data, this illustrates an important point about the current state of observational cosmology. Different datasets probe different epochs and different scales of the universe. They are not always mutually constraining, and they sometimes appear to prefer different values of key parameters. Reconciling these datasets, determining which apparent conflicts reflect real physics versus systematic errors or modeling limitations, is a major ongoing effort. The suite of new instruments coming online in the next decade is designed to probe precisely the gaps in current coverage, producing datasets that will be more constraining than the sum of their parts. The Rubin Observatory, scheduled to begin its legacy survey of space and time in 2025, will photograph the entire accessible southern sky every few nights for 10 years, building a movie of the universe that tracks the variability of billions of objects and maps the distribution of galaxies across a vast volume. The sheer statistical power of this survey will transform measurements of weak gravitational lensing, galaxy clustering, and the properties of transient events, including type Ia supernovae. It will independently constrain the Hubble constant through multiple methods and provide the most comprehensive test of the sigma-8 tension ever assembled. The Square Kilometre Array, a radio telescope array under construction in South Africa and Australia, will eventually provide radio wavelength surveys of hydrogen gas across cosmic history, probing the large-scale distribution of neutral hydrogen through its characteristic emission line. This will add yet another independent measurement of the expansion history and the growth of structure, helping to identify which anomalies in the current data are real and which are artifacts of the optical and infrared wavelengths that dominate current surveys. These are not incremental improvements. They represent changes in the scale of observational cosmology comparable to the leap from Hubble's modest reflector at Mount Wilson to the Hubble Space Telescope. Each generation of instruments has transformed the field, not by confirming what was expected, but by revealing what was unexpected. There is no reason to think the current generation will be different. The Hubble Space Telescope itself, launched in 1990 and operating now for 35 years, has had a scientific legacy that no one fully anticipated at the time of its launch. The most important discovery made with Hubble, the accelerating expansion of the universe revealed through type Ia supernova observations in 1998, was not the primary science goal of the mission. The telescope was designed primarily for high-resolution imaging and spectroscopy of relatively nearby objects. The discovery of dark energy was a bonus, a consequence of having an instrument good enough to make precise distance measurements to distant supernovae. Webb's most important discovery may similarly be something that has not yet happened. Its infrared sensitivity extends our observational reach to the highest redshifts accessible to current technology, to galaxies that existed within the first few 100 million years of cosmic history. Something unexpected may be living in that early epoch that nobody has thought to look for. The history of astronomy is full of exactly this kind of surprise. Radio astronomy, developed in the mid-20th century, led to the discovery of pulsars, quasars, and the cosmic microwave background itself, none of which had been predicted to be radio sources before the instruments existed to find them. X-ray astronomy revealed a hot universe of neutron stars, black hole accretion disks, and galaxy cluster gas that was essentially invisible in optical light. Infrared astronomy uncovered star-forming regions hidden by dust and revealed galaxies in the early universe that optical surveys had missed. Each new wavelength window opened a new perspective on the cosmos. Webb's infrared window, more powerful than any predecessor, has already shown us things we did not expect. The surprises may be just beginning. In the meantime, the scientific community continues its careful, incremental, rigorously verified work. Papers are written and reviewed and challenged, and confirmed. Data are reduced and reanalyzed by independent teams. Models are proposed and tested and modified. The process is slow by the standards of human impatience, but it is reliable. The mistakes that enter the literature are, with time, corrected. The discoveries that withstand scrutiny accumulate into understanding. Adam Rees's Nobel Prize was awarded not for discovering a comfortable fact, but for discovering an uncomfortable one. The accelerating expansion of the universe was a surprise in 1998. It complicated models that were already converging. It required introducing a new unknown, dark energy, into a framework that many physicists had hoped was nearly complete. But it was real, and the field incorporated it, and cosmology became deeper and more interesting as a result. The current tensions may have a similar character. They may be pointing at something real and unknown, something that, when understood, will make the universe make more sense rather than less. The Standard Model, with its successful predictions, is not the final description of reality. It is the current best description, and the best descriptions of the past have always contained within them the seeds of the next understanding. The James Webb Space Telescope is an extraordinary instrument doing extraordinary science. But its greatest contribution may ultimately be this: it is precise enough and sensitive enough to show us, in specific and measurable terms, exactly where our current understanding of the universe ends. That boundary is a gift. It is an address. It is the location of the next discovery. One aspect of the Hubble tension that deserves closer examination is the cosmic distance ladder itself, because understanding its structure illuminates exactly why astronomers are so confident that stellar crowding is not the explanation. The ladder begins with geometric parallax, the most direct distance measurement available. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of much more distant stars. The angle of this shift, called the parallax angle, is directly related to the distance to the star through basic trigonometry. No physical assumptions are needed. No model of stellar physics is invoked. It is pure geometry. The European Space Agency's Gaia satellite, launched in 2013, has measured parallax distances to more than 1 billion stars with unprecedented precision, establishing the first rung of the cosmic distance ladder on an essentially model-independent geometric foundation. These parallax measurements calibrate Cepheid variable stars in the Milky Way. The period-luminosity relationship that makes Cepheids useful distance indicators was originally established statistically, using parallax distances to the nearest Cepheids to set the absolute scale. With Gaia's data, this calibration has been dramatically improved. The relationship between pulsation period and intrinsic luminosity is now known with a precision that would have seemed impossible 2 decades ago. From Milky Way Cepheids, the ladder steps outward to Cepheids in the large and small Magellanic Clouds, our nearest galactic neighbors, at distances of about 160,000 and 200,000 light-years respectively. The Magellanic Cloud Cepheids are important because they reside in well-studied environments and can be observed in detail, providing a cross-check on the period luminosity calibration in a different galactic context. Observations of detached eclipsing binary stars in the Magellanic Clouds, which also provide geometric distance estimates from the laws of orbital mechanics, independently confirm the Cepheid distances to these galaxies. From the Magellanic Clouds, the ladder extends to the Andromeda Galaxy, about 2.5 million light-years away, and then to galaxies in the Virgo cluster and other nearby galaxy groups, at distances of tens of millions of light-years. These are the galaxies where Cepheids can be observed in detail, and where Type Ia supernovae have also been found. The simultaneous observation of both Cepheids and supernovae in the same galaxy allows a direct calibration of the supernova brightness scale. Once calibrated, supernovae can be observed in galaxies hundreds of millions or even billions of light-years away, at distances where the recession velocities are large enough to measure the Hubble constant accurately, removing the contamination from local peculiar motions. This chain has multiple independent checks at each rung. The Cepheid period luminosity relationship can be independently calibrated using parallax, eclipsing binaries, and other methods. The Type Ia supernova brightness can be calibrated not just with Cepheids, but with other techniques, including the tip of the red giant branch, which uses the fact that stars undergo a specific luminosity jump when helium ignites in their cores. Multiple calibration methods give consistent results. Webb's observations have confirmed the Cepheid measurements at the critical junction where blending was most suspected. When all these independent calibrations converge on a Hubble constant near 73, and when this value is inconsistent with the early universe prediction at a significance level that survives every systematic test applied to it, the conclusion that something is genuinely wrong becomes difficult to avoid. The word wrong needs to be used carefully here. The standard cosmological model is not wrong the way a calculation of a wrong answer on a physics exam is wrong. It is wrong in the way that Newtonian gravity was wrong, correct in almost all circumstances it has been applied to, but missing something that becomes apparent only at the edges of its domain. The task is not to discard the model, but to understand what it is missing. One specific physical mechanism that has received substantial theoretical attention involves a modification to the conditions of the very early universe that could affect how the Planck data translates into a predicted Hubble constant. The sound horizon, a specific length scale set by the distance that sound waves could travel through the hot plasma of the early universe before recombination, plays a critical role in this translation. The angular size of the sound horizon in the cosmic microwave background and in the baryon acoustic oscillation scale in galaxies serves as a standard ruler, a reference length whose apparent size tells you about the geometry and expansion history of the universe. If the size of the sound horizon was different from what the standard model assumes, perhaps because the early universe contained an additional energy component that affected the expansion rate during the first few thousand years, then the predicted Hubble constant derived from the Planck data would be different. Early dark energy models work precisely by proposing this kind of modification. A new energy component that existed in the early universe increased the expansion rate briefly and then diluted away before recombination, leaving a different imprint on the sound horizon. The challenge is that any modification to the early universe that helps with the Hubble tension tends to worsen the fit to other aspects of the Planck data. The cosmic microwave background is so well measured that modifying the early universe physics to change the sound horizon affects the angular power spectrum in ways that must also be consistent with all the Planck observations. Simultaneously, finding a modification that solves the Hubble tension without breaking the excellent Planck fit is an unsolved theoretical problem. Every model proposed so far has been constrained by one or more aspects of the data. This constraint is frustrating, but also informative. It means the solution, when found, will have to be a sophisticated one. It cannot simply add or modify one element in isolation. Whatever physical process resolves the Hubble tension must be consistent with every other precisely measured property of the early universe. That is a narrow target to hit, but it also means that when a model successfully hits it, it'll be a confident result rather than a guess. The sigma-8 tension, the other persistent discrepancy mentioned earlier, provides a complementary constraint. Weak gravitational lensing surveys measure how light from distant galaxies is bent and distorted by the large-scale distribution of matter between those galaxies and us. By analyzing the statistical properties of this distortion across the sky, astronomers can map the distribution of matter, including the invisible dark matter, and measure how clumpy it is. The standard model predicts a specific level of clumpiness that should be present in the matter distribution today, based on the initial conditions set in the early universe and the subsequent growth of structure. When three major weak lensing surveys, the kilodegree survey, the dark energy survey, and the hypersuprime CAM survey, compared their measurements to the Planck predictions, all three found slightly less clustering than expected. The discrepancy is at a level of 2 to 3 sigma across multiple surveys. A universe with less clustering than the Planck model predicts is consistent with several physical explanations. Dark matter that is slightly warmer than the cold model assumes would have free-streamed out of small-scale density fluctuations in the early universe, smoothing the distribution of matter on small scales and reducing the clustering amplitude. Modifications to the growth rate of structure, perhaps involving a dynamically evolving dark energy, or a modification to gravity on large scales, could also produce less clustering without affecting the early universe Planck fit. Some models of neutrino mass, the one firmly established form of physics beyond the standard model of particle physics, you could also reduce the clustering amplitude if the sum of neutrino masses is near the upper end of current observational limits. The intriguing possibility that both the Hubble tension and the sigma-8 tension are manifestations of the same underlying new physics is being taken seriously. If dark energy is dynamical rather than constant, it could in principle affect both the expansion history and the growth of structure in ways that shift both tensions simultaneously in the right direction. Finding a single modification to the standard model that resolves both tensions simultaneously while preserving all other successful predictions would be a major theoretical achievement. Nobody has done it yet, which is part of why these tensions remain active research topics. The neutrino connection is worth exploring briefly, because neutrinos are the one particle known to exist beyond the standard model of particle physics, and they play a subtle but important role in cosmology. The three known flavors of neutrinos, electron, muon, and tau neutrinos, were for decades assumed by the standard model of particle physics to be massless. The discovery of neutrino oscillations in the late 1990s, for which Takaaki Kajita and Arthur MacDonald were awarded the Nobel Prize in Physics in 2015, demonstrated conclusively that neutrinos have mass, because massless particles cannot change flavor. This was the first confirmed discovery of physics beyond the standard model of particle physics. The masses of individual neutrino flavors are not yet known, but the sum of the three masses is constrained from multiple directions. Cosmological observations are among the most sensitive probes. Massive neutrinos behave differently from massless ones during the formation of large-scale structure. They stream freely on large scales, suppressing structure formation on those scales, and the amplitude of this suppression depends on how massive they are. The current cosmological upper limit on the sum of neutrino masses is about 0.1 electron volts, which is extraordinarily small by particle physics standards, but not small enough to be negligible in precise cosmological calculations. If the sum of neutrino masses is near the upper end of this range, the suppression of structure growth would be large enough to potentially account for part of the sigma-8 tension. Future cosmological surveys, including Euclid and DESI, may be able to measure the sum of neutrino masses cosmologically rather than just setting upper limits, providing a connection between the tensions in cosmology and the open questions of particle physics. The broader point is that cosmology and particle physics are deeply connected. The universe's early history produced all the particles that exist today. The properties of those particles, their masses, their interactions, their abundance, all left imprints on the observable universe that are still readable today. Conversely, the anomalies in cosmological observations may be pointing at particles or fields that particle physicists have not yet discovered in laboratory experiments. This connection is not new. The discovery of dark matter was, in many ways, a cosmological discovery that particle physicists are still trying to replicate in the laboratory. The discovery of the cosmic microwave background confirmed predictions about the thermal history of the early universe that were rooted in nuclear physics. The abundance of helium and deuterium in the universe was correctly predicted by Big Bang nucleosynthesis calculations that used particle physics inputs. The two fields are unified in the sense that the universe is both the subject of cosmology and the result of particle physics processes in its early history. The Large Hadron Collider at CERN, which will be upgraded to a higher luminosity version called the High Luminosity LHC in the late 2020s, we will continue searching for new particles and interactions in the energy range it can access. Future accelerators, including proposed machines that would operate at energies 10 to 100 times higher than the current LHC, would probe even higher energy scales relevant to early universe physics. Connecting cosmological observations of the Hubble tension and the galaxy formation anomalies to possible new particles or interactions at those energy scales is an active area of theoretical work. Understanding the universe, in other words, is not a project that any single instrument or experiment can complete. It is a collaborative endeavor across multiple fields, wavelengths, energy scales, and generations of scientists and instruments. The James Webb Space Telescope is one chapter in a much longer story. That story began, in the modern scientific sense, with the recognition in the early 20th century that the fuzzy patches of light called nebulae were not clouds of gas within the Milky Way, but entire separate galaxies, island universes comparable in scale to our own, located at distances measured in millions of light years. That recognition, achieved primarily by Hubble's observations in the 1920s, expanded the perceived scale of the universe by a factor of roughly 1 million in a decade. It transformed cosmology from a branch of applied mathematics into an observational science grounded in measurable data. Each subsequent generation of telescopes and instruments has expanded the boundary further. The discovery of quasars in the 1960s revealed that the most energetic objects in the universe, powered by the most massive black holes, existed primarily in the distant past. The development of radio telescopes revealed the cosmic microwave background and the large-scale structure of the universe in a wavelength invisible to human eyes. The Hubble Space Telescope resolved individual stars in distant galaxies and opened the redshift range of galaxy surveys to include the epoch when the universe was less than half its current age. Webb has opened the first billion years, the epoch when the first stars ignited, the first galaxies assembled, the first heavy elements were forged in stellar cores, and the first black holes grew to supermassive scale. What it is finding there is consistent with the broad strokes of the standard model, but inconsistent with its details in ways that are now precise enough to demand explanation. The next generation of ground-based extremely large telescopes, including the 30-meter telescope and the European Extremely Large Telescope currently under construction, will combine Webb's infrared sensitivity with spectroscopic capabilities that can determine the chemical compositions, star formation histories, and kinematic properties of early galaxies in detail. These measurements will constrain galaxy formation models far more tightly than current data allow, and may distinguish between scenarios that are currently observationally degenerate. The question of what the universe is, how it began, How it evolved, and why it has the properties it has, rather than different ones, is the deepest question that observational science can address. It is being addressed right now by dozens of instruments, hundreds of research teams, and thousands of individual scientists, working with the most sophisticated tools in the history of human inquiry. The fact that they have found cracks in their best model is not a failure. It is a success. It means the model is good enough, and the instruments are precise enough to reveal where understanding ends. Where understanding ends is where science begins its most important work. The universe is approximately 93 billion light-years across. The observable part of it, the part from which light has had time to reach us, contains roughly 2 trillion galaxies. The history of those galaxies stretches back nearly 14 billion years. We have been systematically observing the universe for less than a century with instruments sensitive enough to detect anything beyond the Milky Way. We have been observing it with instruments capable of resolving galaxies at cosmic distances for less than 50 years. We have been observing the first billion years, directly, for only the past few. The idea that we might have the full picture after such a brief and recent effort would be extraordinary. The evidence suggests we do not. The data from Webb, and from the measurements of the Hubble constant, are telling us clearly and repeatedly that something in our current picture is incomplete. The next chapter of that picture, when it is written, will be built on the foundation of everything we currently know, extended by whatever new physics the anomalies are pointing toward. That extension, when it comes, will not erase what we know. It will encompass it, the way general relativity encompasses Newtonian gravity, the way quantum electrodynamics encompasses classical electromagnetism. The universe of our current best understanding, with its Big Bang, its cosmic microwave background, its dark matter halos and galaxy clusters, and billions of years of stellar evolution, is largely right. It is just not quite complete. Finding out what it is missing is the work of the next generation of cosmologists, equipped with the next generation of instruments, inheriting the precise and careful measurements that today's scientists have spent their careers making. The James Webb Space Telescope, and the Hubble tension it has confirmed, and the galaxy morphologies it has revealed, are their inheritance. Science moves forward not in leaps, but in the accumulation of precise measurements, each one building on the last, each one narrowing the range of what is possible, until the only remaining possibilities are the true ones. The universe has not run out of things to tell us. It never does. The observational revolution that Webb represents is part of a longer tradition of transformative astronomical instruments. Understanding that tradition provides context for appreciating why the anomalies Webb is finding carry such weight. The telescope was invented in the early 17th century and turned toward the sky in an organized way by Galileo in 1609. His observations of Jupiter's moons, Saturn's rings, the phases of Venus, and the cratered surface of the moon demolished the Aristotelian cosmology that had dominated Western thought for 2,000 years, and initiated the process of placing the Earth within a dynamic, changing cosmos, rather than at the center of a perfect, unchanging one. The Copernican revolution in cosmology began with pointed tubes of glass and ground lenses. By the 19th century, the invention of spectroscopy transformed astronomy from a science of positions and brightnesses into a science of chemical compositions and physical states. By analyzing how light from stars was absorbed at specific wavelengths, astronomers could identify the elements present in stellar atmospheres. They could measure the temperatures of stars, their velocities through the Doppler shift, their magnetic fields. The universe became not just a collection of lights in the sky, but a laboratory filled with matter behaving according to the same physical laws operating on Earth. Photography, applied to astronomy in the late 19th century, extended the power of spectroscopy to faint objects and long exposures, and enabled surveys of the sky at a scale impossible for visual observation. The great photographic surveys of the late 19th and early 20th centuries cataloged hundreds of thousands of stars and nebulae, providing the database from which Hubble and others would make their revolutionary discoveries. The development of radio astronomy after the Second World War opened the sky to wavelengths of light that human eyes cannot see, revealing processes invisible in optical light. The synchrotron radiation of electrons spiraling through magnetic fields, the cold hydrogen gas tracing the structure of galaxies, the thermal emission of galaxy clusters, the cosmic microwave background itself. Radio astronomy gave us quasars and pulsars, and the first confirmation that the Big Bang had actually happened. Space astronomy, made possible by the rocket technology developed in the middle of the 20th century, remove the distorting and absorbing effects of Earth's atmosphere and open wavelengths from X-ray to ultraviolet to far infrared that are completely blocked by the atmosphere. The resulting discoveries, from X-ray binaries and active galactic nuclei, to the ultraviolet emission of hot young stars, to the infrared emission of dust-enshrouded star-forming regions, completed the electromagnetic picture of the universe. Webb is the latest and most powerful chapter in this progression. Its ability to observe at wavelengths from approximately 0.6 to 28 micrometers, spanning the near-infrared and part of the mid-infrared, is not arbitrary. At these wavelengths, the universe becomes transparent to light that would be obscured at optical wavelengths by dust, and the light from the most distant galaxies, Doppler shifted by the expansion of the universe to wavelengths far redder than their original emission, falls precisely in Webb's observable range. A galaxy forming stars in the ultraviolet light of young, hot stars when the universe was 400 million years old, emits that light at wavelengths around 100 to 200 nanometers. By the time that light reaches us, after traveling for over 13 billion years, the expansion of the universe has stretched it to wavelengths of roughly 1 to 2 micrometers. In the near-infrared, where Webb is most sensitive, this is why Webb can see the first galaxies when Hubble could not. It is not just a larger mirror, it is a mirror sensitive to the wavelengths where the early universe appears. The JWST primary mirror, at 6.5 meters in diameter, is more than 2.5 times the diameter of the Hubble Space Telescope's mirror. Area scales with the square of the diameter, so Webb's mirror collects roughly 6.5 times more light than Hubble's. Combined with its infrared sensitivity and its cold operating temperature, which reduces the thermal noise that would otherwise mask faint signals at infrared wavelengths, Webb can detect objects roughly 100 times fainter than Hubble could at the relevant wavelengths. That is the difference between seeing the brightest early galaxies and seeing a statistical sample large enough to draw conclusions. Webb's 4 science instruments, the near-infrared camera, the near-infrared spectrograph, the near-infrared imager and slitless spectrograph, and the mid-infrared instrument, work in complementary ways. The camera takes high-resolution images across multiple infrared wavelength bands simultaneously, revealing morphology, color, and spatial distribution. The spectrographs disperse light into its constituent wavelengths, revealing the spectra of individual galaxies and allowing measurements of redshift, chemical composition, stellar age, and kinematics. Together, they provide a multidimensional picture of each galaxy observed. The near-infrared spectrograph, in particular, has a capability called multi-object spectroscopy. It can measure the spectra of up to approximately 200 objects simultaneously by using tiny shutters, each smaller than a human hair in width, to select specific regions of the field of view. This dramatically multiplied the speed at which Webb can characterize populations of distant galaxies, turning what would have been decades of observing time into years. The result has been a flood of data about the early universe, unmatched in astronomical history. In the first 2.5 years of Webb operations, the volume of spectroscopic measurements of galaxies from the first billion years of cosmic history exceeded the total accumulated from all previous telescopes combined. The statistical sample is large enough now to make statements about populations, not just individual objects. And population statistics are where cosmological models are most powerfully tested. The morphological studies that revealed the prolate, cigar-shaped early galaxies required this statistical power. Individual elongated galaxies could be dismissed as unusual. A systematic excess of elongated galaxies across a well-defined redshift range and mass range is harder to dismiss. The study by Pozzo and colleagues examined hundreds of objects. The signal was present not just in the most massive or the least massive galaxies, but across a range of masses. It was present in multiple independent fields of view, ruling out the possibility that the result was driven by a single unusual region of the sky. It was consistent across different analysis methods. Statistical robustness is the standard by which cosmological claims are evaluated. Single anomalous objects have been found before and turned out to be unusual rather than representative. The little red dots controversy illustrates this. Early claims about their masses were revised when the full spectroscopic picture was obtained. But when a signal appears consistently across a large sample with multiple independent lines of evidence, the probability that it is a statistical fluke or a systematic error decreases rapidly. The elongated galaxy morphologies, the excess of massive early galaxies above the standard model prediction, the Hubble tension confirmed by Webb, and the sigma-8 tension from weak lensing surveys are all examples of signals that have passed increasing levels of statistical scrutiny. They are not going away. They are, if anything, strengthening as the datasets grow. The response of the theoretical community to these observations has been energetic. Dozens of papers have been published in the past 2 years, proposing modifications to standard galaxy formation models, revisions to dark matter models, extensions to inflationary theory, and modifications to dark energy. This activity is exactly what should happen when precise observations challenge a successful model. The theoretical community is doing its job. What the next few years will bring is an increasingly detailed confrontation between these competing theoretical proposals and the expanding observational database from Webb and its companion instruments. Models that can successfully account for the elongated galaxy morphologies will be tested against other Webb observations that were not part of the original fit. Models that reduce the tension with galaxy mass functions will be tested against measurements of galaxy clustering and the intergalactic medium. Models that address the Hubble tension will be tested against weak lensing surveys and baryon acoustic oscillation measurements. This iterative process of proposal, testing, revision, and retesting is how physics advances. It is slow and sometimes frustrating, but it is reliable. The eventual outcome will be a model of the universe that accounts for all these observations simultaneously. And that model will be more accurate and complete than the one we have today. The scientists working in this field are not uncertain about whether the current anomalies are real. They are certain that they are real. What they are uncertain about is which of the many proposed explanations, or which combination of them, will ultimately prove correct. That uncertainty is the frontier of knowledge, and it is where the most interesting scientific work is happening. Every generation of astronomers inherits a picture of the universe that their predecessors assembled. Every generation also finds, somewhere in that picture, a place where it doesn't quite fit together. Their job is to find out why. The picture is then revised, the fit improves, and the inheritance passed on is richer and more detailed than what was received. The physicists and astronomers of the 21st century are working with a picture assembled from 4 centuries of telescopic observation, a century of spectroscopy, half a century of space astronomy, and a decade of measurements precise enough to reveal the seams. They are working with instruments that can see 13 billion years into the past and measure distances to an accuracy of a few percent across hundreds of millions of light years. They are working in a moment when the standard cosmological model, one of the most successful quantitative theories in the history of science, is beginning to show its boundaries. That is not a comfortable position for people who prefer settled answers. But for people who are most alive at the edge of what is known, it is the best possible time to be working. The universe has not finished teaching us. The James Webb Space Telescope is listening, and what it hears, transmitted as ancient light from galaxies too faint for any previous instrument to see, is a story that is more complicated, more interesting, and more surprising than the one we thought we knew. There is one more dimension to this story that deserves attention, because it involves not just the physical measurements, but the mathematical structure of the universe itself, and why physicists find the Hubble tension philosophically significant even beyond its observational implications. The standard cosmological model, formerly known as lambda CDM, which stands for lambda cold dark matter, is built on the assumption that the same physical laws operate everywhere in the observable universe. This assumption, called the cosmological principle when combined with the assumption of isotropy, meaning the universe looks the same in all directions on large scales, underlies every equation in the model. Without it, the equations cannot be solved in their current form. If the cosmological principle is exactly correct, then a measurement of the cosmic microwave background from any location in the observable universe should yield the same prediction for the current expansion rate. The fact that the Planck measurement, taken from our location in the universe, predicts 67, while the direct measurement at our location gives 73, means either the model connecting the early universe measurement to the current expansion rate is wrong, or there is something genuinely unusual about the local expansion rate in our patch of the universe. The possibility that we live in an unusual region, a local void or underdensity that causes nearby galaxies to appear to recede faster than the cosmic average, has been investigated seriously. A sufficiently deep local void could in principle inflate the local measurement of the Hubble constant above the global average. But the surveys of the galaxy distribution around us do not show evidence for a void deep enough or large enough to account for the full tension. The effect, if present, accounts for at most a fraction of the discrepancy. The possibility that the cosmological principle itself is only an approximation, that the universe has genuine, large-scale structure that breaks the perfect uniformity assumed in the model, is a more radical idea. Several studies have found hints of large-scale anisotropy, a preferred direction in the universe at very large scales, in both the cosmic microwave background and in the distribution of supernovae. These hints are at low statistical significance and have not been confirmed definitively. But if confirmed, they would represent a fundamental departure from the foundational assumption of modern cosmology. The implications would be profound. A universe that is not isotropic on the largest scales cannot be described by the current form of the Friedmann-Lemaitre-Robertson-Walker equations that underlie the Standard Model. A new mathematical framework would be needed, one that allows for preferred directions or regions, and the predictions of such a framework for the expansion rate, the clustering amplitude, and other observables could differ from the current model in ways that might resolve some or all of the current tensions. Testing this possibility requires surveys of enormous scale, mapping the distribution of matter and the properties of the cosmic microwave background across the full sky with enough sensitivity to detect anisotropy at a level of a few percent. The Euclid mission and the Rubin Observatory are both designed to provide surveys of this scope, and their data, combined with full sky analyses of the cosmic microwave background, will either detect or tightly constrain large-scale anisotropy. Another possibility worth considering is that the fundamental constants of physics are not truly constant, but have evolved over the history of the universe. The fine structure constant, which governs the strength of the electromagnetic force, the gravitational constant, the speed of light, these are usually assumed to be eternal and universal. But several observational programs have attempted to measure whether the fine structure constant was different in the early universe by examining atomic absorption lines in distant quasar spectra. Some analyses have found marginal evidence for variation, while others have not. If any fundamental constant has changed even slightly over cosmic time, the predictions of the Standard Model, which assumes they are all fixed, would be systematically wrong in ways that could potentially contribute to the observed tensions. Experiments to constrain the variation of fundamental constants will continue to improve in precision in the coming years. They are technically extremely challenging, requiring spectra of distant quasars measured at the highest possible resolving power, but they address a question that is foundational to physics. A confirmed detection of fundamental, constant variation would overturn assumptions embedded in virtually every equation in physics. These more radical possibilities, large-scale anisotropy, varying fundamental constants, modifications to the cosmological principle, are not mainstream explanations for the Hubble tension. The mainstream explanations remain modifications to dark energy, new early universe physics, and warm or modified dark matter. But science is not a democracy. The correct explanation does not win by popular vote. It wins by explaining the data better than any alternative. History shows that occasionally the radical option turns out to be right. The discovery that space and time are not absolute, that they warp and stretch in the presence of mass and energy, that simultaneity depends on the observer, was a radical departure from the intuition of centuries. The discovery that matter and energy are quantized, that particles have wave properties, that measurement changes the thing measured, violated every classical intuition. The discovery that the universe began in a Big Bang and is expanding, rather than being static and eternal as even Einstein initially assumed, was at first considered radical speculation. The cosmological anomalies of the present day may similarly be pointing towards something outside the current conceptual framework, or they may be resolved by relatively modest modifications to the Standard Model. Both possibilities are being pursued. Both deserve to be. What connects all of these possibilities, from the prosaic to the revolutionary, is that they are being evaluated through data, not through philosophy or intuition or preference, but through measurements of the physical universe made with instruments designed to be wrong in as few ways as possible. The scientific method, for all its well-known imperfections and human elements, has no competitor when it comes to producing reliable knowledge about how the physical world works. The universe has been here for nearly 14 billion years. It will be here for a very long time after the last star burns out and the last black hole evaporates. The portion of its history we have observed directly spans the last century. The portion we have observed with instruments sensitive enough to address these deep questions spans only a few decades. In that brief time, we have assembled a picture that is largely correct and precisely wrong in specific ways that are now measurable. That is a remarkable achievement. And the most remarkable thing about it may be this. Every anomaly that has ever been found in cosmology, every measurement that has ever failed to fit the best available model, has eventually led to a deeper understanding. The contradictions have always been resolved. The resolutions have always been illuminating. The universe, in every case, turned out to be more interesting than the model that preceded the discovery. There is no reason to expect the current anomalies to be different. The Hubble tension will eventually be explained. The early galaxy morphologies will eventually be understood. Dark matter will eventually be identified, or gravity will eventually be modified in a confirmed way, or some new ingredient will be found that accounts for both. Dark energy will eventually be characterized in terms of a specific physical mechanism, or the cosmological constant will be derived from some deeper principle, or both notions will be superseded by something better. When that happens, the picture of the universe we have today will be seen in retrospect as the picture that was almost right. The picture that was precise enough and careful enough to find the cracks that pointed toward the deeper truth. The instruments that found those cracks, led by the James Webb Space Telescope and refined by the generations of observatories that will follow it, will be remembered as the tools that open the next chapter of cosmology. The universe is not finished being discovered, and the scientists working on these questions, taking these measurements, writing these papers, building these instruments, are among the most fortunate practitioners of any human enterprise. They get to be the ones who stand at the boundary of what is known and push it further. What lies beyond that boundary is, by definition, unknown. But the boundary itself is visible. The data are there. The anomalies are measured. The questions are formulated. And the next generation of instruments, following in the tradition of 2 centuries of astronomical progress, is being built to answer them. In the end, what Adam Rees said is both a warning and an invitation. We may have misunderstood the universe. 2 flagship telescopes confirm it. The data are consistent. The measurements are real. The model is incomplete. And that is precisely the position where science is most alive. Not in the comfortable territory of confirmed results, but at the edge where what we measure and what we predict refuse to agree. That refusal is the universe pointing at itself and saying, "There is more here than your equations have captured. Come and find it." The James Webb Space Telescope is finding it, one ancient galaxy at a time. Every major observatory that has ever pointed at the sky has sent back surprises. The Herschels, mapping the Milky Way in the 18th century, thought they were near the center of the galaxy. They were not. They were in the outer suburbs of one arm of a barred spiral of a few 100 billion stars. Hubble, measuring galaxy distances in the 1920s, thought the universe was young. It was not. It was old enough to contain ancient stars that needed billions of years to form and evolve. The Uhuru X-ray satellite, launched in 1970, found a sky full of violent high-energy sources that no optical survey had ever hinted at. The COBE satellite, in 1992, found the tiny temperature fluctuations in the cosmic microwave background that confirmed the Standard Model's description of the Big Bang in extraordinary detail. In every case, the surprise came from looking in a new way. Not just looking harder, though that mattered too, but looking differently, at different wavelengths, with different sensitivity, at different timescales. The James Webb Space Telescope is the most powerful example of that principle. It sees wavelengths no previous space telescope could reach with its sensitivity. It looks further back in time than any previous instrument at its resolution, and it is finding, in systematic and reproducible ways, that the early universe does not look exactly like the simulations predicted. This is science at its best. Not confirming what was expected, but discovering what is actually there.